Good afternoon. Before we start, I'm going to take your attendance first. So as I call out your name, please indicate in the messages here, yes, okay, here, or you can just use your mic. All right. Okay. Brenda, are you here, Brenda? Good afternoon. Chan Su Pian, Chan Su Pian, right? Chia Tai Siu, Chia Tai Siu, Chu Zhang Hing, Chu Zhang Hing, right? Okay. Chua Yu Yang, Ernest, Ernest, Goh Kian Sing, okay. Hu Hing Dong, Hu Hing Dong, Khu Bun Kiong, Lau Lok Jing, Lau Lok Jing, Li Zilin, Li Zilin, Lim Chun Wei, Lim Wen Yang, Lim Wen Yang, Yang, Lim Yong Chuan, okay. Long Yao Ting, Long Yao Ting, Lo Tiong Lia, Lo Tiong Lia, okay. Lu Chui Min, right. En Han Xiang, Eng Wei Hong, Eng Wei Hong, good afternoon. Ong Mei Lin, Ong Mei Lin, Peng Shui Wen, Peng Shui Wen, Kwa Yi Han, Kwa Yi Han, right? So Yan Cheng, good afternoon. Tan Shin Sen, Teo Leong Ho, Teo Yi Si, Wong Chung Yi, good afternoon. Wong Ka Shing, Yong Wing Liang, Yong Chie, Yong Chie. Okay, all right, let me just go through one more time. Lim Wen Yang, Lim Wen Yang, are you here? Lim Wen Yang, Lim Wen Yang, Long Yao Ting, Long Yao Ting, Long Yao Ting, Hong Shui Wen, Hong Shui Wen. Okay, all right. Okay, so today we are going to review the materials from week 2 lecture. So week 2 lecture, we looked at GPIO. Okay, so let me go to the notes on GPIO. Lim Wen Yang is here. Okay, all right. Okay, so in the first week, last week, we looked at two things. Number one, we looked at what is a microcontroller. Okay, so you got microcontroller, and inside the microcontroller, you got a processor, and then with this, we can build an embedded system. Okay, and we also know that the microcontroller that we are using is a 32-bit microcontroller because we are using the very popular ARM Cortex-M microcontroller that everyone in the industry is using nowadays. So that's the microcontroller that we are using. And to program the ARM Cortex-M microcontroller, we use a development tool, specifically the Kale Microvision, also very popular development tool. Everyone's using it, so we use that. Okay, so now this week we look at how to program the microcontroller using the development tool. So we know about microcontroller, we know about the development tool. So now we are going to program the microcontroller using the development tool. Okay, Yao Ting, I take your attendance already, yeah? Okay. So how do we do that? The 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 basic way of using a microcontroller is the most basic way is using its I/O pins. So we call this digital I/O. There are two types of I/O. You have digital I/O and analog I/O. What is the difference? Analog I/O means you can input any voltage between VSS and VDD. This is the power supply of your microcontroller. So your microcontroller got VSS and VDD. What is VSS and VDD? In analog circuit, we call that ground and VCC. Okay, so you might be more familiar with this term because when you learn basic electronics or electric circuits, you learn ground and VCC. So Why you call it VCC is because that's the voltage that's connected to your collector. Common collector is the voltage connected to all your collectors, VCC. So anyway, because it's so common, so everyone just refer to power supply as VCC. Okay, but why is it called VDD in digital circuits? Because digital circuits, you don't use BJT, bipolar junction transistors. In digital circuit, we use MOS transistors. So these MOS transistors, instead of base collector emitter, we call it gate drain source. So the voltage supply that's connected to the drain is VDD. All the drains, lots of drains, so VDD. Okay, and the ground is called VSS because it's connected to the source. Right, that's where the D, the C, and the S comes from, and also the E. But this is more commonly known as ground. So for analog I/O, you can input any voltage between VSS and VDD. Only between this range, you can input any voltage. And the microcontroller must have an analog to digital converter to convert the analog voltage that you input to a digital value. Okay, so we will talk about ADC later. That's a later topic. Now we talk about digital IOs. So the digital value, there are only two states, digit two states, binary digit two states. It's either a logic 0 or a logic 1. Okay? And logic 0 is actually a range of voltages. Logic 1 is a range of voltages. Generally, logic 1 is 0.7 VDD to VDD is the range. Generally, it can vary. So this depends on the microcontroller itself, right? The microcontroller's transistor technology. So the exact range of logic 1 for a particular IC, a particular integrated circuit, you have to check its data sheet. So you check its data sheet, you go to the back part, the electrical characteristics. Okay, so for example, I use one that you're very familiar with. I use the PIC16F84A. So you're very familiar with this microcontroller, the PIC16F84A. Just use an example that you're familiar with. So we go to the end of the data sheet. Normally it's at the end. It's called electrical characteristics. Okay, electrical characteristics. So if you go to electrical characteristics at the end of your data sheet, then we look for the voltage range, the voltage range of logic 1 and logic 0. Uh, that's your, there it is. Okay, so this is voltage for input low, voltage for input high. So uh, I think let me zoom in a bit, and let me enlarge, maximize this. Okay, so you can see here, you got input low voltage and input high voltage. So the input high voltage, high means logic 1. The minimum value is 2 to maximum is VDD. 2 to VDD. So what was our value? 70% of VDD to VDD. Okay, so if 70% means if VDD is 5 volts, then it will be 3.5 to 5. 70% of 5 volts is 3.5. Okay, so if your VDD is 3 volts, 3.3, 3.3, then 70% of that will be about 2.3, so 2.3 to 3.3. Okay, so you see the range is not very big now, not very big, because the 32-bit microcontrollers, right? The range for logic 0 and logic 1 is narrower compared to 8-bit microcontrollers, because their timing requirements is higher. You have more data, so you have a lot of timing problems as compared to 8-bit microcontrollers. 8-bit microcontrollers, right? They have a much larger range, 2 to VDD. So in this case, its VDD is between 4.5 to 5.5. This is the test condition, right? While its uh, low voltage, logic 0 is between VSS to a maximum of 0.8. Okay, that means if you feed in any voltage between VSS to 0.8, this device will recognize it as a logic 0. Even 0.7 volts is still considered logic 0. If you feed in 0.81, no, you feed in 0.81 volts, then it's no longer logic 0. And it's not logic 1 either. So the range between 0.8 to 2 volts is unused. Anything you put, if you feed a voltage between 0.8 to 2, it is neither 0 or 1. Okay, so it's not recognized by the digital IC. Okay, so over here, the invalid or undefined range is this uh, uh, grayed out area, right? This shaded area. Okay? So we cannot use this. All right, now VDD smaller, larger, does it make a difference? Yes, it does. That is because your I/O pins, if you look at this, for example here, this I/O pin here, your I/O pin can provide current. If I connect an LED like this, if I connect an LED like this, how do you turn on the LED? The microcontroller is supposed to provide current. So we call this a current sourcing. So where does the current come from? Now your microcontroller has a power supply pin, right? Your microcontroller has a VDD VSS power supply pin. So that's where the power comes from. Okay. So internally, this is a very simplified drawing of the power supply circuit, the your GPIO circuit, your IO port. Okay, this is your GPIO peripheral inside of our controller in a very simplified version. So if you want to supply a logic 1 at this IO pin, then internally this transistor turns on, the upper transistor. If this upper transistor turns on, then the IO pin will be connected to VDD internally, so current will flow out. But there is a limit. So the limit depends on your data sheet as well. There is a limit to the amount of current that you can source. Okay. Now let's look at this example. What is the limit? What is the limit? We are looking for current I. What is the limit? Okay, here. Maximum output current that can be sourced, that you can get from any IO pin is 25 milliamps. Okay, so PIC microcontrollers or 8-bit microcontrollers, they are still so popular because they can supply quite a lot of current, 25 milliamps of current, and their uh, logic 1, logic 0 range is much larger than 32-bit devices. So you see 8-bit devices are still very popular because they are very robust. They can withstand a wide range of operating conditions. Okay, 32-bit, the current sourcing is much smaller. I think maybe 10 milliamps, much smaller. Okay, so that's number one. If you have a higher VDD, you can supply more current. Number two is if you have a higher VDD, then this logic 1 and logic 0 range is bigger. When this range is bigger, then you have better noise immunity. You see, the light blue color is a very noisy signal. The dark blue is what the microcontroller actually sees. So you have a threshold here, right? Whenever this actual signal goes above 2.3, it becomes logic 1, right? It becomes logic 1. If it goes below 1.2, then it becomes goes below 1.2, then it becomes logic 0. Okay, so number one, if with a higher VDD, number one, you get more current. Number two, you get better noise immunity. And is there any other thing? Number three, you get higher switching speed. Why? Because you notice that on your IO pin here, you got two transistors. So these transistors, zoom in a bit. Okay. This transistor, right? Your gate, your drain, and your source, this transistor is it has capacitive effect. So if you want to turn on the transistor, it doesn't turn on instantaneously. That means when you turn on the transistor will need some time, maybe nanoseconds to turn on because you have to charge, you have to charge the transistor. The transistor's gate here doesn't go from low to high immediately. It takes some time to charge because there is a capacitive effect. So with a higher VDD, you can charge faster. So then the transistor can turn on and turn off faster, higher switching frequency. So with a higher VDD, you got higher switching frequency. Okay? But higher VDD also means that you use more power. So there is a balance that you have to strike. Okay? Right. Now, so that's about I/O pins. How do you program the I/O pins? So this is an example of a development board. This is a development board here. Uh, I think this is the KL25Z development board. Okay, this is the one that you saw on week one, the development board that you saw on the week one lecture videos. Right. So what do we have on this development board? Now, the essential stuff that you must have on the development board is, number one, you must have the debugger microcontroller. Okay, so this is your main guy. This is your main target microcontroller. This is the microcontroller that you are using. But beside it, there is another microcontroller. Now, it's not that this guy is very big, this guy is very small. I have to draw this guy bigger to show the stuff inside. Actually, they are the same size, almost the same size. Okay? So this is another microcontroller. This microcontroller holds the debugger program, and the debugger program doesn't change on it's fixed. Okay, you don't program this guy. His program is fixed. He's running a debugging program to allow your host PC, which is running the development tools, to connect and program the target microcontroller. Right. So the target microcontroller, in order to connect to the debugger, it will need some internal support circuitry, right, to support debug connection. Just like a microcontroller, to support connecting to external devices like LEDs and switches, you need I/O pins circuitry. This is your GPIO port circuitry to support this I/O pin to connect to devices. So you have supporting circuitry inside. This is the debug supporting circuitry. Okay, you have two communication languages for debugging, either JTAG, which is the industry standard, or SWD, which is used by ARM. The difference is JTAG uses 4 wires, while SWD uses 2 wires. So SWD uses 2 wires because microcontrollers don't have a lot of I/O pin. So you just need to sacrifice 2 I/O pins for debug connection. And the debugging circuitry is also much simpler. So ARM focuses on lower power consumption and lower cost. Okay, but they also support JTAG. So it depends on which you can choose. The internal circuitry support both. Okay, just that if you use JTAG, you have to sacrifice 4 pins. If you use SWD, you only use 2 pins to connect to the debugger. Okay, all right. So we are able to program the device, and then the device also needs three supporting components, which is power supply, reset, and clock. So all microcontrollers must have power supply, reset, and clock. So let's look at power supply first. This is your external power. External power. So your microcontroller can be, let's say, 3.3 volts. Your microcontroller use 3.3 volts. Very common. 8-bit microcontrollers, they use 5 volts. 32-bit microcontrollers, they use 3.3 volts. This is very common. So power supply, let's say, comes from your adapter. You have a 12-volt adapter, right? 12-volt adapter. So power supply comes in. So you have a voltage regulator here, which converts the 12 volts to 5 or 3.3 volts. Okay, let's say here 3.3 volts, which powers the microcontroller. So a microcontroller has an internal power management circuit, PMU, power management unit, right, which will manage and distribute the power to all the components inside the microcontroller. Now, if you are using host PC, you can also tap the USB 5 volts to power your microcontroller. So then you don't need an external power supply. Okay, for very low power applications, you're not controlling motors, all right? You're just switching some LEDs and some LCD screen. Then the power from the USB is enough. Okay, this is your reset button, reset button. So reset is active low, reset is active low. So when you press the reset button, the reset circuitry will connect to ground. It will connect to ground, and then the mouse controller will go into a reset state until you release the button. When you release the button, the logic state of this pin will be pulled up back to logic 1, and the mouse controller can run again. And then you have clock management. So you need an external oscillator. Now, internal oscillators, they are great. They are great if you have an oscillator inside the mouse controller. Internal oscillators, they are great. But the problem with internal oscillators is they are not so accurate. Okay, they have a variation, plus minus, not so accurate. So if you have some very timing critical applications where you need the time to be really accurate, then you need an external crystal oscillator. So this oscillator is actually a crystal material. It's a crystal material with piezoelectric properties. Piezoelectric property means when you apply a voltage, that's why you got two pins. When you apply a voltage on this piezoelectric material, it will start to vibrate. And when it vibrates, it will vibrate at a very, very specific frequency. The material is engineered to vibrate at a certain frequency. And that's why you call it oscillator. So the clock management circuit will apply a voltage on this crystal material, which will vibrate and generate frequency, for example, 12 megahertz. So this crystal is engineered to vibrate at 12 megahertz. So generate 12 megahertz. Now 12 megahertz is not very high. That's because internally, the clock management circuit will multiply the clock so that your processor can run at a much higher clock speed. Why do that internally? Because internally we can have very high frequency, no problem. If you have a high frequency outside, you're going to create a lot of digital noise. So we don't put, let's say, 100 megahertz oscillator outside. That's going to make a lot of digital noise on your circuit board. So we do that inside. Outside, we just have something that's not too high, like maybe 8 megahertz or 12 megahertz, very common. Okay, all right. So we got our power, we got our program in already, we can reset, and we got clock already. So once the program goes in, what happens is the mouse controller will start executing the program to do some control function. Now let's say your control function is regarding I/O pins. So how do you program the I/O pin? Four steps. Four steps. Step one, you have to enable the clock. Because microcontrollers, they want to save power. So to save power, you uh, block the clock from reaching the circuit. Okay, you see this GPIO circuit. If it doesn't receive any clock, then it's not running. When it's not running, it's not consuming power, or it's not doing anything. So in order for it to run, step one, you must enable the clock signal to reach the circuit. Step one. So now it's running already. Then step two, you have to select which internal peripheral to connect to the I/O pin. Because ML controllers, we have very limited I/O pins. We don't have a lot. Okay, you don't have a lot of I/O pins because the more I/O pins you put in, the bigger the chip is going to be. And when the chip is bigger, it's going to cost more. So and it's also going to make your circuit board very big. Okay, so the number of I/O pins is minimized to make the whole IC smaller. But because of this, then you don't have a lot of I/O pins. You have to sacrifice the I/O pins. Right? That's the disadvantage. You don't have a lot of I/O pins. So we have a multiplexer here, I/O pin multiplexer, where you can select. You have a lot of internal peripherals connected to this I/O pin. So you want to select which of the internal peripherals you want to connect to this particular I/O pin. Okay? That's what we call the I/O pin multiplexer. So the I/O pin by default is connected to the GPIO, right? It can be connected to other peripherals. like your ADC or PWM module. But you need to program the IOP multiplexer, step 2. Then, step 3, you have to configure this GPIO peripheral. You have to configure it to work as input or output or some other functions. And finally, step 4, you have to program interrupts, right? Interrupts are the basis of microcontroller response. Microcontrollers are, except for the most simplest application, we don't keep checking whether something has happened or not. We don't keep checking. We don't write a forever loop to keep checking. We just use interrupts. So if something happens, then the interrupt is generated. And we have to program the interrupt. So that's step 4. Program the interrupt. So when the GPIO detects something, it will just generate an interrupt to the CPU and the CPU will respond. Okay, so step 4 steps, 1, 2, 3, and 4. Now, this is the general flow of programming the IO pin. But how do we actually program it? We have to use pointers because the microcontroller's peripherals are all programmed through registers, right? Like this. I just used the pig mount controller as an example only. You see, if your pig mount controller, if you want to program the I/O ports, then you got two registers, right? You got port A and trice A. So these guys are 8-bit. You got port A and trice A. Then you have to set or clear these bits in order to program this I/O port. Okay, in order to set or clear bits in these registers, you have to know its address. You have to know where the register is, its address. Okay, and since we are programming in C language, we use pointers. We use pointers. So we set a pointer to point to a particular memory location, and then we can access that pointer to read or write from that memory location. Okay, so I don't talk much about pointers because you already learned pointers in C++. Anyway, pointers just allow us to read or write from a particular memory location if we know the address. Okay, so let's do some actual programming. So here in this example, we do some actual programming. In this example, uh, so this is a LPC1768 microcontroller. This guy very popular. Why we use this guy is because this LPC1768 microcontroller, he's the first microcontroller come out using Cortex M3. You got a few different Cortex models. So Cortex M3 is the general purpose guy, the most general purpose. Okay, general purpose microcontroller. So this LPC1768 is the first microcontroller that used the Cortex M3 processor. Okay, so we want to blink this LED. This LED is connected to port 1 bit 18. I want to blink this LED. So it's just a very simple job of put this to logic 1 and to turn on the LED, put this to logic 0 to turn off the LED, right? Very simple job. And we, of course, we have to put a resistor here to limit the current. So how do we do it? So now, just like the PIC, you program the port A tries A. So for this guy, you have to program uh, DIR, FIO DIR, FIO mask, FIO pin, FIO set, FIO clear. So each IO port, you got 5 registers. Okay. Now this comes from the user manual. So if you want to see the user manual, LPC1768 user manual. Okay. LPC1768 user manual. Let's go to the GPIO, right? So you see it's pretty much the same. It looks just like your PIC microcontroller data sheet. Actually, they're all standard one. So we look at the GPIO. Okay, I just want to show you where you can get all this information only, right? GPIO, general purpose IO. Okay, so we scroll down a bit. We scroll down a bit, and we see that okay, this microcontroller got how many ports? Port 0, port 1, port 2, port 3, port 4. How many bits? Port 0 got bit 0 to bit 30, 31 bits. Port 1 got 0 to 31, 32 bits. Port 2 got 14 bits. Port 3 only got 2 bits, bit 25 and bit 26. And port 4 only got 2 bits, bit 28 and bit 29. Okay, so not all IO ports got 32 bits. It depends on. So okay, so how do I control these IO ports? How do I set or clear a particular IO pin? Then we look at the control registers. So we scroll down here a bit. So these are the control registers. So you got FIO-DIR. So you got the FIO-DIR for port 0, FIO-DIR for port 1, FIO-DIR for port 2, port 3, and port 4. And these are their addresses. Okay. FIO-DIR controls the direction, input or output. So how you know in more detail? Then you scroll down a bit. We look in detail at FIO-DIR. Okay. So this is FIO-DIR. If you put a 0 on a particular bit, then that pin is an input. If you put a 1, then that pin is output. Okay. So this is the same for all the registers. Just refer here. Now I go back up. Okay, I go back up. And we see that you have a total of 5 registers. FIO-DIR to set the direction, FIO mask to set clear or read, right? FIO pin. Oh, you can mask out certain bits. So let's say the port got 32 bits, right? You can use FIO mask to disable. Mask. Mask means cover, block, disable. You can disable certain pins using FIO mask. FIO pin, you can set or clear a particular pin using FIO pin. FIO set is only to set, FIO clear is only to clear. What is the difference? Why I got FIO pin, I can set and clear? Why I still need FIO set and FIO clear? That's because of if you use FIO pin, you have to use a few clock cycles to you have to use a few clock cycles to uh, change the value of the pin. Okay, if you use FIO pin means you have to read the current state of the pin, modify it, and then write it back. We call this read, modify, write. Read, modify, write. If you use FIO pin to set or clear the state of an IO pin, you have to use a few cycles. You have to read the state of the pin, modify it, and then write it back. But if you use FIO set, you don't have to read. You want to set the bit, you just straight away set, write a 1, you'll become 1. Right? FIO clear, if you want to clear the bit, you just write a 1 to that bit, you immediately clear it. Okay, so FIO set and FIO clear is for atomic operation. Atomic operation means that you complete the operation of setting or clearing the bit in one cycle. No disturbance. You cannot be interrupted. This is very important because we want to avoid race conditions. Race condition. You remember in computer architecture, race conditions can happen. If you are doing something which requires a few clock cycles, you may be interrupted in the middle of doing it because the processor can receive interrupt requests. So let's say the processor is doing a read modify write operation. If you use FIO pin, you do a read modify write operation. Halfway of you read already, you modify already, you haven't write back yet. You haven't written back yet. There is an interrupt. Then the processor will run the code for the interrupt service routine. It may affect your read modify write and make what you're doing wrong. Okay, because you can be interrupted. Okay. For example, imagine I give an example. Let's say now you are you are eating something. So you need to look at the food, scoop it, and then put in your mouth. Look at the food, scoop it, and put in your mouth. Okay, and the food which is, let's say, the processor. So now you look at the food. Oh, it's noodles. Okay, you're going to scoop already. But right before you scoop, or you get interrupted. Okay, so the noodles then went and do something, and it changed to become rice. Okay, then you continue back with what you were doing. Then you scoop, and then you eat. When you eat, why is rice? It's not noodle. Because the thing that you're doing, the data can be changed by other processes. So if they change the data, if they interrupt you and change what you're doing, then what you're doing might become wrong, right? That's why you have FIO set, FIO clear on top of FIO pin. So these guys, they are all here, right? So you got the FIO DIR mask pin set clear. This is for port 0, and these are their addresses. Okay, you got for port 1, port 2, port 3, and port 4. So how do we access these guys? We use pointers. So now we see how we use pointers. Okay, so to use pointers, all you need to do is write the code like this. This is all you need to do. So you define FIO1 DIR as this whole thing. Okay, what is this? Right. So this is the address. This is the address. Okay, and this is pointer. So let's break this down step by step. Now, unsigned long means 32-bit, a 32-bit container. Okay, unsigned char means 8-bit container. Unsigned short means 16-bit container. Unsigned long means 32-bit container. So unsigned long, I have a 32-bit container. When you put a star here, it means you are creating a pointer to a 32-bit container. Pointer to a 32-bit container. And then you put the address. This is the address of the pointer. Okay, so I've created a pointer to a 32-bit container with this address. And then I close everything in the bracket and I put another star here. When you put another star here means you access the memory location that the pointer is pointing to. Okay, and you see this whole thing is like very long, so I don't want to keep writing this. So I hash define. I tell the compiler I want to replace this whole thing with a simple word FIO1 dir. So now whenever you use FIO1 dir, you are actually accessing this location. Okay, so if I want to put logic 0 there, I just write FIO1 dir equals 0. Then I can clear this whole location. Okay, but the thing is, this is not very user friendly. The reason is because you see I got 5 IO ports, port 0, 1, 2, 3, 4, and each port got 5 registers. So 5 IO port with 5 registers each, 5 times 5, I need 25 addresses. Okay, so I have to declare, if I use this method, I have to declare 25, I need 25 hash defined lines. I need to create 25 pointers, 25 32-bit pointers. Oh, that's a lot of memory. Now imagine you got 100 peripherals in your microcontroller. So you need a lot of memory. So is there a better way to do this? Yes, we use data structures. So data structures is like this. Okay, data structures is like this. So I define a data structure. I define a data structure as a derived data type. Right? Type define means you can create new data types, inverted comma, not really new, inverted comma, new data types from existing data types. So these are all the existing data types. Okay, I can uh, create I can create a new data type which is a combination, a hybrid of existing data types. So okay, I create a structure with these members inside FLDIR mask pin set clear. Now I can do this because in a structure, right, all the members have consecutive memory addresses. That means one after the other, which is true. Okay, if you look at the memory addresses, their memory addresses are consecutive. 048C10141816 consecutive. So I can use the data structure to do this because the locations are consecutive, right, one after the other. So what I do is, after I've created this data structure with type GPIO type def, then I declare a pointer to this data structure and I give it this name. So GPIO 0 now points to the data structure for port 0. and you have port 1, 2, 3, and 4. So instead of creating 25 pointers, I only need 5 pointers. That's a 80% save in memory, right? I save 80% of memory just by doing this. So if you want to access how, we can access members in a structure using the dot operator or the arrow operator. What's the difference? If the name of the data structure is a pointer, or we say the identifier of the data structure is a pointer, then we use arrow operator. If the identifier of the data structure is a name, it's not a pointer, it's a name, then we use the dot operator. Okay, that's the difference. Now, uh, we can we can read or write smaller sizes if we use unions. What do we mean by smaller sizes? Okay, now you notice here, FIODIR, right? If I access FIODIR, I have no choice but to access the entire 32 bits. What if I don't want to access the entire 32 bits of FIODIR? I just want the lower bits or the uppermost 8 bits or maybe 16 bits. So we can use union. So using a union, I can uh, I can create one container that can store data of different sizes. Okay, so here I have a container that is 4 bytes in size. I have a container that is 4 bytes in size. So this container, I can access all 32 bits of data at one go, right? Like this. If I declare a union, unsigned long A, so A allow me to access all 32 bits at one go. If I want to access the lower 16 bits or the upper 16 bits, then I can use AL or AH. Okay, so this is a union of a 32-bit number together with two 16-bit numbers and four 8-bit numbers. So I can access either the 32-bit value, upper or lower 16 bits, or any of the bytes, any of the 8 bits inside here. Okay, so this is how I use unions to allow access to smaller portions of a particular container. In fact, you can even access bits. Okay, you can also create a structure here, another structure where you can individually access each of the 32 bits inside this entire container. You can do that using bit fields. Okay, right. So that's structures and unions. And lastly, this is structures and unions inside your header file. So all microcontrollers, when you create a new project, uh, the development tool will automatically insert a header file for you. So this header file contains the names of all the registers. It contains the name of all the registers. So you don't have to manually create pointers. The pointers are all already created for you in this header file. You just need to look for the name of the pointers. So it makes use of structure and unions together, okay, to save memory and also allow you to access different sizes of data within the same container. Right? This is just one example for the FIODIR. You can access the entire FIODIR 32 bits or separate 16 bits or individual 8 bits. Okay, so that's all. And now let's look at quiz. Let's look at quiz 2. Let's look at quiz 2. Okay. Oh, I already answered it. Okay. How come it's already answered? All right. Okay, what is the advantage of macro over function? What is the advantage of macro over function? Now, macro and function, they are both methods used for uh, reusable code. Let's say in your program, you have a few lines of code that you keep reusing. So rather than writing these few lines of code every time you want them, why not group them together as a function and just call the function? Okay? So that's how you use reusable code. But the thing is this, if you use it as a function, whenever you call the function, you need to spend a few clock cycles to branch to the function. And after you finish with the function, you have to spend a few clock cycles to return from the function. So sometimes you cannot sacrifice this delay. Sometimes you need something to happen really very fast. You cannot sacrifice this delay. So rather than writing it as a function, you jump there, okay, you use a macro. A macro is also called an inline function. Inline function. What it means is the the function code is copied and pasted where the macro or inline function is called. So whenever you call a macro or an inline function, right, the entire code is copied and pasted there. When you build, when you compile the program, the entire function code is copied and pasted there. So let's say in your program, you call this function 10 times. That means this function, this code will be copied and pasted at the location where it's called 10 times. So no branching. You don't sacrifice clock cycles to branch and return. But the price that you have to pay is you use more memory. Okay? So advantage is reduce program execution time. But does it reduce code maintenance time? No. Macros and functions, they are the same. They help you to reuse, make your program more readable, more maintainable. Okay, so they are both the same. Reduce memory usage? No. Actually, macro use more memory, right? Reduce possibility of coding error. Macros and functions both do the same thing. Help make your code easier to understand and maintain. So it would be advantage is reduce execution time using macros. Okay. Next one, which is not in a typical device header file. Not in a typical device header file. So in a typical device header file, you will have the register layout. You will have the register layout. Just now you saw the FIO, the structure. You saw the structure just now. So that's the layout of the register. So you got register layout, and then you got register address, and you got access definition, name of registers. Okay, now what is not inside the header file is peripheral configuration. This one you have to write yourself. That means you configure the peripheral. For example, you configure the I/O port to be input or output. Okay, this one you have to configure in your application code. It's not in the device header file. Okay, right. Next one. Uh, okay, we are going to initialize the GPIO. Which step is the least essential, the least important, least useful? Interrupts up. Okay. First of all, the most important, you must enable clock signal. Then you must connect the peripheral to the I/O pin. Then you need to configure the peripheral. Okay? Interrupt is optional. Sometimes you don't need to use interrupts if you're just polling. Right? You write a simple loop to keep checking the status so you don't have to use interrupts. Okay? So this is the least essential, which is not an effect of increasing VDD. If I increase VDD, I'm going to get greater noise immunity. Yes. I'm going to get greater sourcing current. Yes. I'm also going to consume more power. Okay? But switching delay is going to reduce. When I increase VDD, I have more current. I can charge and discharge the transistor faster. Okay? When I increase VDD, I can charge and discharge the transistor faster, so the transistor can switch faster. So the switching delay will actually be smaller switching delay. Okay, right, so this is not an effect. All right, next one. Uh, what is the purpose of using volatile keyword? Why do we want to use the volatile keyword? Now, just now I didn't talk about the volatile, so I just go back there now. Volatile. Okay, so here is an explanation of why we need to use the volatile keyword. Now, if you look at this programmer, let's look at this programmer, right? This is for an 8-bit microcontroller to keep things simple. So I got an 8-bit microcontroller with two registers, rec1 and rec2. So I declare rec1 as unsigned char, 8 bits. I declare rec2 as unsigned char, 8 bits. So I got two 8-bit peripheral registers. Okay. Then I write a function where I check rec1 bit 0. Okay. So this is a while loop. The condition is rec1 AND with bitwise AND with 0, 0, 0, 0, 0, 0, 0, 1. Okay, so I'm checking bit 0. So this condition will become true if rec1 if rec1 bit 0 is a 1. If rec1 bit 0 is a 1, when you AND with this value, then the result is a 1. True. Okay. So if rec1 bit 0 is a 1, then I'm going to keep looping here indefinitely. As long as rec1 bit 0 is 1, I'm going to keep looping here. What do I do when I loop here? I'm going to toggle rec2 bit 7. This one, bit 7. 8 is 1, 0, 0, 0, 0, 0, 0, 0. I'm going to toggle bit 7, 0, on, off, on, off, on, off, on. This is my intended behavior. I want the system to behave like this. But you know what happened is, the compiler, right, is very smart. The compiler will try to produce as little assembly code as possible. Because the compiler's job is to change your C program, convert it to assembly instructions. A good compiler will produce the minimum number of assembly instructions. Not so good one will produce a program of a larger size, use more memory. Now this is quite significant because your microcontroller, right, have limited flash memory, non-volatile memory to store program. It has limited memory. So if the compiler is not good, then you might run out of memory. Okay, your program is too long, you run out of microcontroller memory. So you need a good compiler. So for the compiler to reduce the size of the program, it does what we say optimization. It performs optimization. Optimization means it removes whatever is not necessary. How does it decide? Okay, if you see here, the compiler look at this. Okay, this one we will check rec1 bit 0. Rec1 bit 0. Now, the compiler look at this program and see, did anyone ever change rec1 bit 0? No. Nobody set or change rec1 bit 0. Then it will check, what is the value of rec1 bit 0? Now, let's say the default value of rec1 bit 0 is 0. Let's say the default value of rec1 bit 0 is 0. When you turn on the microcontroller, is 0. So if I do this, 0 and with whatever, it will always be 0, right? So the compiler will think, this piece of code will never run because this condition will never be true. So this whole piece of code is removed. The compiler discards this entire piece of code, so you don't get the behavior you want because the compiler thinks that this will never happen. Now, but the truth is this will happen. Why? Because we actually connected a push button to this rec1 is an IO port. Right? We connected a push button to bit 0. So when we press the button, we actually change the state, but the compiler doesn't know this one. So how do we prevent the compiler from performing optimizations on certain variables? We add the volatile keyword. When you add the volatile keyword, you are actually controlling compiler behavior. You tell the compiler, do not optimize any read or write to this variable, so that the intended behavior will remain. Doesn't change. This is the intended behavior. Okay, so that's what volatile is for. Okay, so what is the purpose of using the volatile keyword? Optimize multiple access to a variable. No, this optimize multiple access to a variable is you use the load multiple instruction instead of load one data. Okay, so controlling compiler behavior. Okay, this is correct. Indicate data loss on reset. No such thing. Ensure correct program behavior. Not accurate. So the most accurate would be control compiler behavior. Okay, so that the compiler doesn't perform any optimizations regarding read or writes to this particular variable. Add the volatile in front. Okay, next one. Uh, which is the most useful function of pointers in microcontroller? The most useful. So they are all useful, but the most useful would be accessing registers. Okay. Specifically in microcontrollers, the only way that you can access, if you do C programming, the only way that you can access peripheral registers is by using pointers. Okay, so it's an efficient coding method. Okay, it can allow you to have efficient memory usage, but pointers are not the most useful. Uh, Now you cannot access core registers. This is because core registers do not have address. Okay, you use pointers to access registers that have address. If the register don't have an address, you cannot access them. Core registers are the registers inside your processor. They don't have address. What are registers inside your processor? The registers inside your processor is your status register, your program counter, your these are the common ones. Uh, your instruction register, and so on. Okay, these are the common ones. Registers inside your processor, we call them core registers. They don't have address, so you cannot use pointers to access them. How do you access them? Assembly. That's why assembly language is still around, because you need assembly language to access processor registers, to read the status register, read the program counter, and so on. Okay, right. Uh, what's the difference? What's the difference between structure and union? Structures and union are identical, except for the way they store things. So structure store things sequentially in memory, sequentially in memory, one after the other. Union store everything in the same container. A union allow you to store members of different sizes, but all inside the same container. So member storage is the difference. Okay? Member size, no difference. Member access is point is using the arrow operator or dot operator, no difference. Right? Member type also no difference. So it's the way they are stored. Okay. Last one. What is the disadvantage of using IO pin multiplexing? Now, if I use IO pin multiplexing, less size is an advantage, right? Your mouse controller is smaller. That's an advantage. Less cost. That's an advantage, right? That's an advantage. Uh, Less flexibility. Um, IO pin multiplexing is actually give you more flexibility, not less flexibility. Okay, why? Because if you use IO pin multiplexing, you notice if you use IO pin multiplexing, you can actually choose. You can actually choose which which peripheral connect to this IO pin. Okay, now it's very useful because your microcontroller. Let's say I want to put an LCD on this side. To connect to the LCD, I need a few wires, right? If I can choose which peripheral to connect to these IO pins, then I can make the wiring of my microcontroller to the external components simpler. That means my printed circuit board, the wiring design is simpler because I can adjust which peripheral connect to which IO pin. Okay, so that's what we mean by flexibility. Okay, so the disadvantage would be you have less pins. You have to sacrifice on the number of IO pins. So the number of IO pins that is available is less. So that's the disadvantage. Okay. All right. Class, do you have any questions before we stop here for today? Everyone okay? All right. So if no questions, then we will stop here for today. Okay, thanks everyone for coming. Okay, you're welcome. All right. Okay.